class, we've learned that the electric force can be found using the equation Fe equals K times the magnitude of Q1 times the magnitude of Q2 divided by the distance between the two charges squared. And we've also done some simple examples using two charges, finding the force that one exerts on the other. But what happens if we have multiple charges? That's commonly the case. A two-charge example is actually fairly rare. So in this video, we're going to go over how to find the electric force on a particle, on a point particle, which means it's very small, and that force will be caused by two or more charges, two or more point charges once again, so very small charges. To learn how to do this, we're going to learn by an example problem. Basically, you'll find that what we do is we end up adding vectors. So we'll start with this first example problem. We're looking for the magnitude and direction of the electric force on each of these three charges shown. In this video, we'll go through how to find the force on only one of the charges, and then the other two will be for you to do on your own. So we've got three charges here. I'm going to label them A, B, and C so that it's easier to talk about them. So we'll together find the total electric force on charge A, which I'll call F sub A. The first step when you have multiple charges is to find the force that each charge exerts on the one in question. In other words, I'm going to find the force that B exerts on A and the force that C exerts on A. Notice that I am using vector symbols now. That means that I need to pay attention not only to magnitude, but also to direction. We'll go over exactly how to do that. For starters, I'm going to find the magnitude of the force that B exerts on A. Notice that the way that I use those subscripts is important. The force that B, that's my first letter, exerts on A, that's my second letter. That's the order of subscripts that we will always use. Well, we know the equation is K, the constant, times the magnitude of QA this time, since I'm calling that charge A, times the magnitude of QB divided by R squared. So let's plug some numbers in. We've learned that K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. QA, the problem tells us, is 6 microcoulombs, or 6 times 10 to the negative 6th coulombs. And QB is 1.5 microcoulombs, so 1.5 times 10 to the negative 6th coulombs. The distance between them is 3 centimeters, or 0.03 meters, and we can't forget to square that denominator. As I plug those numbers into my calculator, I end up getting that force BA has a magnitude of 89.9 newtons. We'll do the same thing, but now we're calculating the force that C exerts on A. Just the magnitude once again. So we still have the same K value, 8.99 times 10 to the 9th, Newton meters squared per Coulomb squared. We still have the same charge for A, that's 6 microcoulombs, but now we'll use the 2 microcoulombs as the charge for C. Again, I'm ignoring that negative sign. And I'm also converting. Going back to my diagram up here, I see that the distance between A and C is 5 centimeters. I have to convert that before I plug it into my equation here. So I have 0.05 meters, and I can't forget to square that. Plugging that all into my calculator yields a value of 43.15 newtons. So the first step is to find the magnitude of these two forces that end up making up the total force or the net force on charge A. The next step is to look at the direction. And to look at the direction, I'm going to go back to my diagram up here. Starting with the force that B exerts on A. Well, I know that if B was hammered down in place, B is not allowed to move. But if I allowed A to move, A would move to the left because A and B repel each other. Again, I'm kind of ignoring C right now. So B is nailed in place. A is able to move to the left. Therefore, that force is pointed to the left. I'll indicate that with an arrow and put a vector symbol on top of my force. For finding the direction of the force that C exerts on A, I pretend like B doesn't exist. Like it's a simple problem with two charges, A and C. One is positive, one is negative. Since I'm looking for the direction of the force that is exerted on A, then I want to think about how A would move if C was nailed down. Well, if C was nailed in place, A would move toward it because they're attracted to each other. That means that A would move to the right. So the direction of this force is to the right. My last step is to add together these two forces to get the net force on A. Now we know that when we add parallel vectors, we have to pay attention to their direction. Since they're parallel, I can use a negative sign to indicate pointed to the left. So I'll plug in a negative 89.9 newtons and a positive sign to indicate to the right, 43.15 newtons. As I add these two numbers together, I end up getting a total value of negative 46.75 newtons, which means in a final answer format, I would write 46.75 newtons left, indicating that that negative sign means that that force is in the leftward direction. So we now have found the net force on charge A. The problem tells us to find the net electric force on each of the charges. So it is now your task to find the net force that's exerted on B and the net force that's exerted on C. We'll go over what these values are in class. We're going to move on to another problem. This problem, once again, has three charges, but you'll notice that they're in a different configuration. Instead of all being in a straight line, we have them in kind of an L shape. We'll go through and talk about in this problem how that changes the way that we approach this problem. One thing that doesn't change, however, is that I'm going to start off by labeling my three charges. And I'm going to label them A, B, and C, similar to in the last problem. Once again, we're asked to find the magnitude and direction of the electric force on each of the three charges. I'll stick to doing A, just like I did before, and then your task, once again, will be to do B and C. So I'm trying to find the net electric force on A. To do that, that net electric force on A is going to be the sum of the two forces that are acting on A. The force that B exerts on A and the force that C exerts on A. Unfortunately, unlike in the previous problem, these two forces are not parallel to each other this time. Just as in the previous problem, our first task is to calculate some magnitudes of forces. So we'll calculate the magnitude of the force that B exerts on A, and then we'll do the same thing for the force that C exerts on A. We know that our equation is K. We have the magnitude of QA times the magnitude of QB over R squared, Plugging some numbers in, we know K is equal to 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. QA, the problem tells us, is negative 3 nanocoulombs. Since we have those absolute value signs, I'm going to ignore the negative, and I need to get rid of the nano. Nano is 10 to the negative 9th. So this is 3 times 10 to the negative 9th coulombs. Similarly, I'm going to plug in 5 times 10 to the negative 9th coulombs for B, and the distance between them is 0.1 meter, and of course I have to square that. Plugging that into my calculator, I get a value of 1.35 times 10 to the negative 5th newtons. Looking at magnitude only once again. In the same way, I can find the force that C exerts on A by multiplying 8.99 times 10 to the 9th Newton meter squared per Coulomb squared by 3 times 10 to the negative 9th coulombs, and times the charge of C, which is 6 times 10 to the negative 9th coulombs. The distance is a little trickier this time. And I say that because we're not given the distance. We need to find the distance between A and C, which would be this straight line distance right here. Fortunately, we can use the Pythagorean theorem to come up with what that distance is. Now, I have to have the distance squared in the denominator. So instead of actually calculating the distance this time, I'm just going to do 0.1 squared, 0.1 meters squared, plus 0.3 meters squared. That ends up giving me that distance squared, which is actually what I need to have in my denominator. It's also perfectly fine for you to actually calculate that distance. Plugging all this into my calculator yields a value of 1.62 times 10 to the negative 6th newtons. Now we need to look at direction. In the last problem, it was easy. The direction was either to the left or to the right. So we were able to assign a positive or negative sign and then just add our values. It's not quite that simple this time. Looking at the direction of the force that B exerts on A, I'm going to ignore C, pretending like C does not exist in this problem at all. Since I'm looking for the force on A, I'm going to nail B down. B is not allowed to move. And I want to think about what direction A would move. Well, A and B are oppositely charged, which means they're attracted to each other. So A would want to move toward B, which is in the positive y direction, or up. I can now consider this to be a vector. Looking at C and A, again, I pretend as though B doesn't exist, since I'm only concerned with the force that C exerts on A. And I pretend like C is nailed down and is not allowed to move. And I look at the direction that A would travel. A is attracted to C, so A would want to move toward C. Well, that's not in the x or in the y direction explicitly. Rather, that's at an angle. So when we have something like this, where the force is at an angle, we need to find x and y components. So we're going to look for FCA in the x direction and FCA in the y direction. This is going back to our knowledge of vectors. It's been a while since we've done that. Because A is attracted to C, this force vector looks something like that, with a magnitude of 1.62 times 10 to the negative 6th newtons. We are trying to find the x and y components. So there's my x component and there's my y component. Now, before we can actually find those components, we need to know an angle. Specifically, we need to figure out what this angle right here is. To figure out that angle, I'm going to use the concept of similar triangles. I know that we have a distance of 0.3 meters and a distance of 0.1 meters. And that triangle that I just drew right here, which you can see basically the inverse of in my diagram up here, would be a similar triangle. Without even knowing the value of the hypotenuse, I can calculate this angle right here. And that'll be the same as the angle for my force. I'm going to use the inverse tangent to do that. So theta is equal to the inverse tangent of 0.1 meters divided by 0.3 meters. Of course, you need to make sure that your calculator is in degree mode. And when you do so, you should find that the angle is 18.4 degrees. That helps us come up with those x and y components. The x component is the adjacent. So the cosine of theta, looking at my diagram up here for the forces, the cosine of theta would be the x component divided by the hypotenuse. That means that the hypotenuse times the cosine of theta, which is 18.4 degrees, will give us the x component, which is what we're looking to find. When I plug that into my calculator, I get an x component of 1.54 times 10 to the negative 6th newtons. That is a positive x component because it's pointed to the right. Similarly, I'm going to find the y component, but in this case, I'm going to use sine instead of cosine. 1.62 times 10 to the negative 6th newtons times the sine of 18.4 degrees. And I'm choosing to use sine because the y component is the opposite component, and sine is opposite over hypotenuse. That gives us a y component of 5.12 times 10 to the negative 7th newtons. Once again, a positive value because it's pointed upward. Just a note on how I found these values. Even though when I write them on the board up here, they are rounded, when I use the values in my calculator, I just use the number on my calculator instead of the rounded value. So if you used rounded values, your number might be slightly different than what I have written here. Okay, so now we have some values that we need to add. We have two components there, and only one value for the force that B exerts on A. But that's because we know that that is only in the y direction. The force that B exerts on A in the x direction is equal to 0. So just as we have done with vectors in the past, we'll need to add the x components and add the y components. When I add those components together, I find that the x component of the force exerted on A is 1.54 times 10 to the negative 6th newtons. Similarly, the y component gives me 1.40 times 10 to the negative 5th newtons. Both of those components are positive. My last step is to then add together as vectors these two components. That means that I'm adding this positive x component which is fairly small. It's times 10 to the negative 6th. Adding that to this positive y component, which is fairly large, that's times 10 to the negative 5th. Notice that the y component is almost 10 times larger than the x component. Clearly my scale is a little bit off. I'm adding those two to get my resultant, which I just drew in red. Well, to find the resultant, I'm going to use the Pythagorean theorem. X squared plus y squared equals the total squared. And when I do that, I find that the net force on A has a magnitude of 1.41 times 10 to the negative 5th newtons. It's pretty similar to that y component, since that y component is so large. Then I need to find a direction. Based on how I drew my diagram here, I always find the direction at the tail end of my resultant vector. So that would be the angle that I marked there. I suggest using tangent because that doesn't mess with the number we just calculated. If I use tangent, or rather inverse tangent, I would use 1.40 times 10 to the negative 5th newtons divided by 1.54 times 10 to the negative 6th newtons. And that yields an angle of 83.7 degrees. And then we have to say where that angle is, which you may say ISP, above the positive x-axis, or north of east. This is my final answer. These problems take a while, but it's not much different than adding vectors, which we've been doing for a long time. So once again, on your own, your task is to attempt to find the force exerted on B and the force exerted on C. You'll find that finding the force exerted on B is one less step because the two component forces are perpendicular to each other. So we don't have to find components of them. And then finding the force exerted on C will be very similar to what we did for the force exerted on A. Don't forget to pay attention to direction of each of these forces, which you can find based on figuring out if they attract or repel each other. We will go over the answers to the total force on B and the total force on C in class.